All right, now we're going to look at aquatic ecosystems and how things affect the environment in the water, in lakes and streams, and even the ocean. But we're going to look at a lake specifically just to give you a smaller scale to look at. But remember that these principles apply on a large scale as well and to any aquatic ecosystem, although maybe in a slightly different way for each one. So to start off with, you need to know these two terms. And the first one is what's called an oligotrophic lake. An oligotrophic lake is something like Waterton. Now this is not Waterton, this is Lake McDonald down in Glacier. Maybe some of you have been there. But you can see just by looking at it, it looks very similar to Waterton or similar kind of mountain lakes. Oligotrophic lakes tend to be deep, they tend to be very cold, and they tend to not have a lot of nutrients, which is the low nutrients and the cold temperature you can see is why they tend to be very clear. There's not a lot of plant, algae, other growth happening in the lake. And so we end up with this nice, beautiful, clear water as a result of those things. Another characteristic of oligotrophic lakes, because they're so cold and because they're so clear, they have typically quite high levels of oxygen. So fish that thrive in high oxygen environments, very active fish like trout and things like that, they do very well in these kind of lakes. So in Waterton, there's lake trout, there's whitefish, there's rainbow trout. Those fish love this kind of a lake or the streams that feed from these kind of lakes because that water holds enough oxygen to allow them to survive. On the far other end of the scale, we have eutrophic lakes. These lakes tend to be more shallow. They tend to be a little bit warmer, higher levels of nutrients, and you see more plant life, more plant growth, more kind of algae and moss and that kind of stuff growing on the surface. And the water tends to be more of a murky, kind of a, not nearly as clear to look at in a eutrophic lake. So those are the two kind of extremes we're looking at. You've got deep, cold, nutrient-rich water in the oligotrophic lakes. You've got shallow, warm, nutrient-rich. Did I say the oligotrophic was nutrient-rich? It's nutrient-poor, oxygen-rich. Eutrophic is nutrient-rich, although it tends to be more oxygen-poor. And we'll talk about two reasons why. The first one for right now is just temperature. Warm water doesn't hold as much oxygen, just like warm pop doesn't hold as much fizz. It's flat. Even if it's right out of the can or the bottle, if it's warm, it's not very good. So cold lakes hold more gas than a warm lake. So this lake, even if it was just warmer, won't have as much dissolved oxygen. The other thing that leads to low oxygen we'll talk about kind of at the end of this video. But for now, you just need to know these two terms, oligotrophic and eutrophic. Now there is a process of natural eutrophication where lakes gradually over time will move from oligotrophic towards eutrophic. Now that process could take hundreds or even thousands of years to happen, but it can happen naturally where maybe the rivers that run into this lake bring in every spring a little bit of sand and silt. You've probably seen even Lee Creek. It's kind of a brown color in the spring with all the runoff and sediments. Well, that sediment ends up in the lake, and over a long period of time, it eventually fills that lake up. And now instead of being a deep lake that can maintain pretty cold temperatures, now it's a much more shallow lake, and the sunlight now maybe hits all the way to the bottom. Maybe we don't have that profundal zone anymore, and so the temperature of the body of water goes up, the oxygen content goes down, and the species present may change in that lake as well as a result of that. Now, this is a natural process that can take a really long time, but human activities can also mess this up. So things that we do will lead to lakes like this, where maybe it wasn't an oligotrophic lake, but a fairly clear natural lake is going to become much more eutrophic because of human impacts. And the ones in your notes that you need to make sure that you are kind of aware of are, the first one is organic solid waste. Typically there we're talking about feces, whether that's human or whether that's manure from a feedlot, from animal kind of operations. But those solids run off or maybe blow in the wind and they end up in the water, and that's going to cause some changes. We can also get disease-causing organisms. So from, let's say, a cabin or an outhouse on a lake, sometimes that the waste that's sitting below that outhouse can leach out and get into the groundwater, which eventually could feed into the lake. So a friend of mine, for example, in BC, he had a trailer on a nice lake, and last year they shut down the beach because they found out that some of the stuff from like the outhouses and people's trailers had leaked into the water, and now the water was contaminated with bacteria and all sorts of stuff that could make people quite sick. So they had to shut the entire place down because of those wastes, those disease-causing organisms getting in there. The next one is inorganic solids and dissolved minerals. This one is kind of, I mean, in a broad term, think fertilizer, although there's other solids and things that might be included here. This could be natural, like phosphorus cycle or nitrogen cycle getting into the water, but it could also be over-fertilizing or just runoff from fertilizer. Maybe a farmer did a great job of fertilizing responsibly, but then there was a really heavy rain and some of that water washed down from his field into the stream, which led to the lake. And fertilizer does the same thing in a lake as it does on the land. It makes photosynthesis happen better, faster. And so now this lake is going to suddenly start to become more eutrophic because there's more plant growth and more things like that going on there. Next one is thermal energy, and thermal just means heat. So let's say we pull water out of Lee Creek and then it runs to all of our houses, it goes down the drain, it ends up at the water treatment plant, and then it goes eventually, once it's cleaned up and processed properly, it goes back into those bodies of water like St. Mary's River. But let's say we pulled it out of the creek and it was 8 degrees Celsius. If we put it back into Lee Creek at 12 degrees Celsius, we've added heat, we've added thermal energy to that body of water. And so now a lake or a stream may start to become more eutrophic just because we're adding in that much more heat, which means there's going to be less oxygen in the water, which means that's going to have an impact on a lot of things, kind of a cascade reaction that we'll talk about in a little bit here. But even just that change in temperature can lead to this, where certain things are now growing better, or certain things are not growing as well, right? Less oxygen because the water's warmer could affect trout and other species like that and lead to changes that way. And the last one is just other organic compounds, things that are out there, and that would include things that may be good, that increase plant life, but it could also be things that are bad, that are negatively impacting the environment in one way or another. Okay? So those are some of the things that we do that can cause these lakes to become more eutrophic. So one of the things that is really important to do is to monitor water quality. Now, I don't mean that just for the water that you're drinking or in your house, but the quality of our lakes and our streams. Are they changing? Are there things that we're doing that are negatively impacting these ecosystems? And what can we do to either fix it or to try to prevent the damage that may come from some of these human activities that we just talked about? Now, one of the ways that we do that is by testing for things like bacteria. It's really expensive, though, to test for bacteria, at least for all of the different types of bacteria, especially in a developing country where we want to make sure there isn't disease-causing things in the water. It's expensive to test for all of those different bacteria in the water. One that's a little bit cheaper to test for is what was called coliform bacteria, though. And that bacteria is something that lives and thrives in the intestines of humans and most other mammals as well. So if there were, that test is cheap and easy. So if we test the water and there's coliform bacteria in that water, the only way that could have got in there is if somehow feces is getting to the water. That could be animals upstream that are just pooping in the river. That could be a feedlot that's near a river where there's runoff that's getting into the body of water. It could be contaminated groundwater from from a septic system or from an outhouse or something that's leaking into that system. But we definitely know if you have coliform bacteria, something is getting in the water. And even though we can't do the more expensive tests, we can say that something for sure is wrong. And then we could investigate to try to find where the cause or the source of it was to be able to try to fix the situation. One of the other things that we test for quite often is dissolved oxygen. Now, dissolved oxygen doesn't look like this. This is just bubbles. But in these bubbles, there is some of that oxygen that's dissolving into the water itself. So you wouldn't see it. It's just in there for the fish to be able to breathe, to be able to access. Pardon me. And we can do chemical tests to measure how much dissolved oxygen is in the water, but that takes equipment and some scientific know-how to know how to operate the equipment. But one of the easier ways to do it is we can just monitor the species that are living in a body of water to see what the oxygen is like. So for example, around here, if you have trout living in a body of water, you know that there's a high amount of oxygen because they're a very active fish. They need a lot of oxygen, so they'll thrive in that kind of environment. If it's a little bit lower, like down in the south where they have more eutrophic warm lakes, you're going to have things like carp and catfish. Around here, a warmer lake, you're probably going to have something like pike, a fish that's not as active as a trout. It tends to do a little better in those kind of warmer environments. Not like warm, because this is southern Alberta, but warmer than, say, Waterton. And if you just have a complete absence of fish, then that tells you that something is very wrong. There's not very much oxygen in that environment at all. Now, this is not from around here. This is from another lake. But you can see in that body of water, they've kind of classified what can live at different amounts of dissolved oxygen. So if you have 6 milligrams per liter of dissolved oxygen, then striped bass is fine. 5 milligrams per liter, that's what the white perch, yellow perch, American shad, and hard clam need. The alewife, the bay anchovy, the crab, and then the spot, and then the bristleworm. So you could actually look at this lake, for example, and let's say you showed up one day and you noticed a bunch of striped bass had died. They were floating in the water, and maybe a few yellow perch. Well, that could be an indication that there's a toxin in the water, but it could also be an indication that your dissolved oxygen levels are starting to drop below 5 milligrams per liter. And so maybe they're dying not because of some toxin, but maybe just because there's not enough oxygen in that body of water. So we can use this as a way of, without doing actual measurements or tests on the water, we can use this just to do some observations to determine whether we think the oxygen content of the water is dropping or whether things are going pretty well. Now, biological oxygen demand explains why eutrophic lakes, the other part of why eutrophic lakes don't have very much oxygen. And this is kind of a complicated definition, so we'll look at that and then I'll explain sort of what it means. So it's the amount of dissolved oxygen needed by decomposers, which are typically bacteria in the water, to break down the organic matter in a sample of water over a 5-day period at 20 degrees Celsius. Now that's long and complicated. Just think of it as the demand, how much oxygen is needed to break down or decompose the stuff that's in that water. So if you've got a body of water, let's say like a eutrophic, or let's say an oligotrophic lake, let's start there. There's not a lot of plant life. There's a few fish and their wastes, but because there's not a lot of plant life, there's probably not a lot of decomposition that needs to happen there. So the only demand for oxygen would be the fish themselves. The biological oxygen demand for those bacteria would be very, very low, which means that the oxygen doesn't get used up by them. It gets left in the water for the trout and the other fish. If you move to a eutrophic lake, though, there's a lot of plant growth. And all of that plant growth is going to do a couple of things. One, it can block out the sun and actually choke out some of the other plants that grow on the bottom of the water. But they also are all things that are going to eventually die, and that leaves more stuff in that water that needs to decompose. So you might think that a body of water with lots of green stuff in it would have more oxygen because of photosynthesis. But in reality, more stuff growing in the water means you need more bacteria and more decomposers to break that stuff down. They demand more oxygen. And the decomposers can actually use so much oxygen that the oxygen level of the lake starts to drop. And fish and other species can actually be choked out and die, or at the very least be not as much less healthy than they would have been because there's not enough oxygen left in that body of water. So those processes that we talked about where humans are causing eutrophication of a lake, as the lake becomes more eutrophic, the biological oxygen demand goes up. That demand is consuming more of the oxygen in the water as well as it warming up. So the amount of oxygen is going to drop in that body of water, and that's going to negatively impact probably a lot of those, especially those higher oxygen demand kind of species like trout and things like that around here. So some of the changes that we see in Alberta lakes and maybe lakes that your family frequents or visits, you may have noticed things like the water level dropping either through drought or poor water management. The lakes are just running out of water. In some cases, as the lakes get lower, not only is the shoreline farther away from where it used to be, but because there's less water, they become more salty. We call that salinity, or the measure of how much salt is there. It's the same amount of dissolved stuff, but just now it's in a smaller body of water. And so the lake is becoming a little bit more salty, not ocean salty or Dead Sea salty, but enough that it could start to negatively impact some species and even some of the plant life that grow there. Or things like, especially with cottages, if they're not well built, the runoff from outhouses or campgrounds or things like that getting into the water, at the very least bringing some of those dissolved organic nutrients and organic solids to the water. And on the worst case, even things like parasites and bacteria and things that are going to influence the ecosystem as well. So that's some of the impacts and the changes that can happen to aquatic ecosystems. Remember, we looked just at lakes, but this could also apply on a more large scale to even oceans or on an even smaller scale to streams. So very similar processes happens in all of those cases with aquatic ecosystems. So if there's anything here that you struggle with or that I didn't make very clear, if I kind of stammered through something, don't hesitate to send me an email or a message and just ask a question. I'll try to clear things up as much as I can. But hopefully this makes a little bit of sense to you. And yeah, we'll catch you on the next one.